Hello there and welcome back. We are continuing on with our lessons on optics. Today's lesson is all about mirrors and reflection. So you may have played around with mirrors in the past, and you may have noticed that if you put an object in front of a mirror like yourself, there will be an image on the other side, a reflection, and that would look a lot like yourself. What you might not have had the chance to do though is play around with curved mirrors. If you could imagine like a fun house or something like that, if there's a curved mirror, then the reflection that you get from that curved mirror can be quite different. It can be upside down, it can be quite large, or it can be small, or in fact it can be right side up and very large. And all these different things can be explained through something called the law of reflection. So whenever light strikes a surface, whenever it goes from one medium into a new medium, there's kind of one of three things that can happen. The light can be reflected from the surface, it can bounce off, it can refract or move through the surface, or it can be absorbed. And so in this lesson, we're going to talk about what happens when we bounce off, when light bounces off a new medium. And so when light is reflected from a material, in particular a plane, like a flat surface, it follows the law of reflection. So the law of reflection basically says that the angle of incidence equals the angle of reflection. That is to say that when light comes in, it bounces off at the same angle. We sometimes just abbreviate this as angle of incidence is theta I equals theta r. Now, it's important to note that when we measure these angles for reflection, these angles are measured from the normal. So there is a normal line from any plane surface, which is just a line perpendicular to the mirror or to the plane. So perpendicular. So let's see an example of that. Now, for today's lesson, you're going to be using a ruler or straight edge, so make sure you have one handy. Imagine we've got a nice reflective surface, like a mirror or a window, or maybe even just like a really glassy pond or whatever you happen to be gazing into. And so imagine that there's a series of rays of light that travel towards this surface. Now, these rays of light are all parallel to each other as they travel towards the reflective surface. So they kind of all go in this direction here. Now when they bounce off, the incident angle is going to equal the refracted angle. So if I imagine this last ray of light here, I could draw a normal line right here. There's my normal. And the normal line is just perpendicular to the surface. And so this angle here, my angle of incidence, is going to have to equal this angle here, my angle of reflection. So when I draw my reflected angle, my refracted ray, I should say, I should travel off at the same angle that I came in at. Now, because this surface is reflective, like a mirror or what have you, since all of these rays came in towards the mirror parallel to each other, they're all going to bounce off also parallel to each other. So this is going to give us something called specular reflection, which is all the reflected rays bounce off in a really predictable sort of pattern. But if you imagine another flat surface, like a piece of paper or a wall that's painted or whatever, even though it's flat, and it certainly looks very flat, if you were to zoom in very close, you would see that the surface is not perfectly flat, that it would actually have all these sort of irregularities on it. And so when the rays of light come in towards that surface, and even though they come in all parallel, they are going to strike the surface and they're going to bounce off in all sorts of irregular directions. And so this is diffuse reflection. So it is true that even if we have different surfaces, whether it's mirrors, plane mirrors, curved mirrors, or even irregular surfaces, reflected light does follow the law of reflection. It's just that if the surface isn't perfectly flat, then those normal lines aren't all aligned. And so they're not all going to bounce off in a nice regular sort of repeating sort of way. So one thing we're going to do in order to understand what's going to happen when light bounces off of a mirror is we're going to draw ray diagrams. So when we draw ray diagrams, what we're doing is we're gonna pick an object and then look at how light moves off of that object and then bounces off of the mirror and how it behaves. So first thing we're going to look at is plane mirrors. So by plane mirror, I just mean a flat mirror. When you have a reflection off of a plane mirror, the first thing to notice is that the reflection itself, or the image, I should say, that's formed by the reflection is the same size. And it's also the same distance behind the mirror that you are in front of it. So for example, if I look at my reflection in the mirror, however tall I am, that's how tall my image appears to be. And however far in front of the mirror I am, that's how far behind the mirror my image appears to be. Now the image is also right side up. So by that I mean if I'm standing upright, when I look at my image, I'm upright, but it is laterally inverted. And so by that I mean that the image is flipped in this way. And so if I had a t-shirt on, when I'm looking at my image, I might notice that the logo is flipped around backwards. Or if I wave with my right hand, my image appears to be waving with their left hand. And it is important to notice that when we have reflected light, that the reflected light, it reflects off at the same speed, the same wavelength, the same frequency. Those things don't change. So imagine, for example, we wanted to draw an array diagram for a simple plane mirror. So there's my mirror in the center. Okay, and I've got a really simple image, which is just a smiley face. Okay, so I've got a smiley face. Now, what's this going to look like? Sometimes the way we draw this is to draw an observer. We kind of draw an eyeball, like looking at the person or the object, whatever it is. And then, so in order to understand what this image is going to look like, I'm going to draw rays. Now, it's important to note that rays of light bounce off of this smiley face and go in all directions. So I could draw rays of light going in any direction I want, but I'm just going to choose the ones that are going to allow me to figure out what's happening in the simplest way. So for example, if I pick like a ray of light that starts here on the top of my object, it's going to travel towards the mirror, something like this. It's going to travel towards the mirror, and then it's going to strike the mirror and bounce off at the exact same angle it came in at, and then strike the eyeball over here. You can notice there that my angle of incidence and angle of reflection are equal. If I choose another point, like for example, maybe I choose the bottom. So I'm going to choose a ray of light that comes from the bottom of the object. It's going to travel towards the mirror. So I'll just draw a nice straight line. Okay, go in a straight line. And it's going to bounce off the mirror and it's going to strike the eyeball, something like that. And again, it's going to follow that law of reflection. So, of course, notice that the rays of light bounce off the mirror and hit the observer. But what does the observer see? Well, the observer, to them, it appears as though the image is behind the mirror. So I can carry these reflected rays. These reflected rays as they bounce off, I can carry them back behind the mirror. So if I use my ruler, I can kind of imagine a little dotted line here. Okay, so that ray, that lines up with behind the mirror if I follow that ray in a straight line. And I can do the same thing with the bottom of the bottom ray, so the ray that came from the bottom of the object, and you can see it kind of goes here. And what we would see is that, well, where those lines line up, I could see that there's the top of my object, and there's the top of my image and the bottom of my image. And so now I just kind of fill in the blanks, and then my smiley face appears to be here. Okay, and of course those smiley faces should look the same, but that's not the point. So with the ray diagrams, the key insight here is we can just pick whatever lines we want, draw them going off of the object, following our laws of reflection, our law of reflection, and then where those objects travel behind the mirror or in front of the mirror will give us some indication about what the image is going to look like. And you can see this image is upright, it's the same size, it's laterally inverted, if you could tell that from my picture, and so on. So really where this is going to be useful is in understanding curved mirrors and how reflections work from those things. So the first thing to recognize, there's two kinds of curvatures. We can have concave or convex. So I always think of concave as being like caving inwards, and concave as being so I always think of concave as being kind of caving inwards and convex as being not concave. But the other way to think about these mirrors are being either converging or diverging mirrors. So imagine for each of these cases, what I want to think about is if I had three rays of light that were parallel and traveling towards them. So I'm just going to draw three parallel rays going towards the mirrors and then striking them kind of like this. So striking the mirror like that. Okay, awesome. Okay, so these are the incoming rays or the incident rays in each case. Now, what is going to happen when they strike the mirror? Let's think about the concave mirror first. I'm just going to draw the reflected ray in a different color. Of course, the color of light will not change, but this will just help us kind of visualize what's happening. Well, for the concave mirror, right in the center, even though it's curved like this, my normal line right in the center is going to be straight up and down. That's kind of the normal line. It's perpendicular from the center of the mirror. So when this ray of light bounces back, it's going to bounce back in a way where it just bounces basically straight back like this, okay? And that's nice and simple. But what about this ray over here kind of on the left side? Because the mirror is curved, because it follows this curvature, the normal line at that point is not straight up and down. The normal line here is going to be kind of pointing in towards the center. And so I'm still going to follow my law of reflection, where my angle of incidence equals my angle of reflection, and it's going to look something sort of like this. So you can see that ray of light is going to bounce inwards. Now what about over on the right side? Well, the normal line is going to be kind of in this direction here, if you will, and I'm going to follow the same rules I did before. So my normal, or my reflected ray, is going to kind of go this way and along like that, and bounce in. What you should notice is it certainly looks like this concave mirror, those reflected rays are coming together, and that's true because this concave mirror is also a converging mirror. So it might be helpful to think about that as it converges the light to a single point, to a focal point, as we'll talk about in a second. The convex mirror, by comparison, when I look at that central ray, it's going to behave similarly as it did with the concave mirror, where it's going to bounce, the reflected ray is going to bounce kind of straight back. Okay, that's pretty straightforward. But what about this ray over here on the left? Well, because the mirror curves the way it does, my normal line looks something like this, which means that my reflected ray is going to bounce off in this direction here, like something like that. Okay, and the same thing over on the other side. So my normal line kind of angles away from the center, if you will, and so my reflected ray is going to bounce off kind of like that. Okay, now you can see here that those reflected rays are never going to meet. That's because this is also known as a diverging mirror. Now we're going to talk about lenses later on, so it's probably useful to think about these terms converging and diverging, as well as the convex, concave. Now, when looking at these mirrors and lenses, as we're going to learn in a bit, there's kind of four terms that we want to be aware of. There's the principal axis, and the principal axis is just a line that runs through the center of the mirror. So line through center of mirror. Okay, and we'll see what that looks like in just a second, but it's just an imaginary line that helps us kind of keep everything organized. Now our center of curvature, which we're going to label as capital C, it is the center of the circle. If you imagine that a curved mirror is cut out of a larger circle, the center of curvature is the center of the circle that makes up the larger mirror. Now, circular mirrors aren't actually perfect at focusing light. In actual fact, you would want parabolic mirrors to focus light to a really specific point. But again, for our purposes, exactly how perfect the mirrors are isn't going to be a big deal. The focal point is capital F. And it's the point where all of the rays converge. So it's the point where rays converge. So if I have a converging mirror, then when the light strikes it, it's going to focus those light rays at a certain point. And the focal length, last one there, focal length, we give it the symbol lowercase f, is the distance to the focal point. So the distance to the focal point. Now, it is worth noting that if I have a circular mirror, the focal point is located, or the focal distance is exactly half the center of curvature. So the center of curvature is located 2 focal points away from the mirror. Okay, so we're going to draw just like a whole bunch of examples of these ray diagrams, and what we're going to try and understand is, what is the image going to look like depending on where my object is and what kind of mirror I'm working with. And again, I just want to jump back to this example I had here. So if I have a curved mirror, you can see that depending on where I put my object, I get a very different looking image. Sometimes the image is over here in front of the mirror, sometimes it's behind the mirror, sometimes it's really big, sometimes it's small. So we want to understand all of that. Now again, something I just want to point out, that when I go back to my plane mirror here, notice how my plane mirror, my object is always behind, my image is always behind the mirror. Well, rays of light are coming off of this object in all kinds of directions. So there are like zillions of rays of light traveling in all directions, and I could spend all day long drawing all of them, but that's actually not going to really help me understand. It's going to be more work than is necessary. So all I really need to do is draw just a few rays of light. And so that's what we're going to do. Of course, we could draw more, but we're going to try and draw as few rays of light as possible to understand what's going on with this reflection. Now, if I jump back to my curve mirror, again, in this case, there are lots of rays of light that I could draw, but I'm only going to draw a few, and these are the 3 rays that I want to focus on. We're going to imagine what would happen if you had a ray of light, like this first one here. This ray of light travels parallel to, you can see this principal axis here, this dotted line. So this ray of light travels parallel to the principal axis, and you can see it bounces through the focal point. Another ray of light travels through the focal point, strikes the mirror, and bounces back parallel to the principal axis. And then there's a third ray that we can draw or even just check with our ruler, which is if I travel from the object and strike the center of the mirror, then the angle of incidence here should equal the angle of reflection, and I should bounce right back at the same angle. Now notice that these points meet, that those rays meet at a point. That is going to tell us where our image is. So whether I'm close or far or really close, where those reflected rays meet, that gives me the indication of where my image is and a bit of information about it. Okay, so let's try that. So let's first just imagine I've got a concave mirror here, and I'm just going to pick a focal point. So it doesn't really matter what you choose, but I'm just going to choose something nice and consistent. So I'm going to draw my first focal point here, which is 3 centimeters from the mirror, which means my center of curvature is going to be 6 centimeters. So I'm just going to make sure that part's consistent. So I'm going to label this first diagram center of curvature and focal point. Might as well put all the other things in here just so we're clear. This right here, that's my focal length, the distance to the focal point. And then right along here, this line that runs through the center here, there's my principal axis. Okay, and it's just a line, imaginary line that runs through the center of the mirror. And so I'm going to put my object, in this case, the object is beyond the center of curvature. So I'm going to pick an object that's easy to draw, thankfully, and then I'm just going to put that, I'm going to start that beyond my center of curvature. So for this first object, I'm going to choose a Christmas tree. Okay, so here we go. There's a tree. Beautiful. All right, and it's located beyond my center of curvature. Okay, so remember there were 3 rays that I could draw, and I only actually have to draw 2 of them. 2 is the minimum that I can draw and know where my image is going to be. So the first one, the first ray, is going to go parallel to the principal axis. And remember that if it goes parallel to the principal axis, then it will bounce off through the focal point. Okay, so what does that look like? Okay, so I'm just going to use my ruler and I'm just going to draw a line which goes parallel to the principal axis and strikes the mirror, something like that. Okay, so if it's parallel to the principal axis, then it has to bounce off through the focal point. So I'm going to bounce back this way, and you can see I'm going to line up with where it strikes the mirror, and I'm going to line up with my focal point, and I'm going to draw a nice straight line. And I'm going to draw that line like a good long way. I don't know how far it needs to go, so I'm just going to kind of continue it on because I don't know how far it needs to go. Okay, my second point here that I need to draw here is the second point is going to go through the focal point. Now, if I go through the focal point, then I need to bounce back parallel to the principal axis. And this gives you an idea of why this is called geometric optics, because we just follow a set of geometric rules. And if we follow these rules, then, well, we get predictions about what our image is going to look like. So now I'm going to imagine that my ray goes through the focal point like this. Okay, so there's my other incident ray, and it is going to have to bounce back parallel to the principal axis, because that's the rules. Okay, that's how the focal point works. Now, at this point, that's all the information I need because I've got my two lines. Notice that where the points meet, okay, so where those 2 points meet, that tells me where my image is. Now, specifically, the top of the tree, remember that those rays came from the top of the tree, which means the top of the image has to be located right here. So the top of my tree image is there. Now, I could do this whole process all over again for the bottom of the tree, but I cheated a little bit, or at least I was smart about it, where I put the bottom of the tree right on the principal axis, which means any ray that comes off the bottom of the tree is going to strike the mirror and bounce straight back, which means the bottom of the tree is going to be right here, also on the principal axis. Well, I can see the top, where the top of the tree is and where the bottom of the tree is, so I just need to fill in the blanks, okay? And so this is what my image is going to look like. Now, take a look at that image. There's a few things that we can notice about it, okay? The first thing that we should notice is that the object is inverted, okay? It's upside down. The second thing you might notice is that it's smaller, okay? It's smaller than the object is. The third thing you might notice is that it's located between C and F. So whenever I've got an object that starts off beyond C, my image is going to be between C and F. And the last thing, which you haven't learned about yet, is that this image is real. This is a real image. Now, what does that mean? A real image is one where the rays actually converge at a single point. So these rays bounced off the mirror, they were separate, and they came back together. So they actually converge. Or another way to think of it is it could be projected on a screen. So it could be projected. It does not mean, if the image isn't real, it doesn't mean that you can't see it. It just means that the rays actually come together. They start at a certain point and they come back together at another point. We're going to see that sometimes the reflected image is virtual. And while you can see it, the rays never actually converge in the same place again. Okay, so we're going to follow these same rules for each of these situations to predict what the image is going to look like in each case. Okay, so our next example here is going to be to consider an object located between C and F. So I'm going to do the same thing to set this up. I'm going to draw my focal point. And again, you can choose any distance you want as long as you choose a consistent distance, as long as the focal length is the same between the focal point and the center of curvature. As long as those are the same, you should be fine. So what happens if the object is between C and F? Okay, so I'm going to draw for my next object, I'm going to draw a lovely candle. Don't ask me why, but there we go. I've got a candle in front of the mirror. Okay, so I'm going to follow the exact same rules I did last time, and then I'm going to use that to predict where my image is going to be. Okay, so the first line I draw is parallel to the principal axis, coming off of the top of my candle, parallel to the principal axis. So it goes like this. That is going to bounce off through the focal point, and so something like this. Okay, very nice. So there's my first ray. Now my image is somewhere along that ray. I just don't know where yet. The second line I'm going to draw is going to be through the focal point. So I'm going to start on top of the object and I'm going to go through the focal point. Now it is important to notice that this is geometric optics. So if you're ever doing this and your mirror just isn't big enough, you can just pretend your mirror is a little bit bigger. That's okay. It should still work out. So this ray that travels through the focal point is going to bounce back parallel to the principal axis. So something kind of like this. All right, so there's my reflected ray. Now, just like I saw before, so again, you can see that the top of the image is going to be located here. And I, at this point, wishing I'd chosen something easier to draw than an upside down flame, but that actually turned out okay. So the top of my flame is right there, but the bottom of my candle is on the principal axis. And so here's where I can kind of fill in the blanks of what this looks like. Now, take a look at this. What do we know about this case? Well, there's 4 things we can notice again. Number 1, my image is inverted again. Okay, so my image is inverted, that's for sure. The second thing to notice is that the image is beyond beyond C. So it's further away than it was before. The third thing to notice is that it is larger. So my image is actually larger than it used to be. And then the last thing, it is still real. So again, we're maybe not quite sure what we mean by that, but the rays of light actually converge at a single point. And so that is a real image. Okay, so now let's imagine what happens if we are within the focal point. Okay, so within the focal point F. And so again, I'm going to draw my starting position. So I've got a 3 and a 6 centimeters there. So there's my focal point, and then there's my center of curvature. And so I'm going to draw an object that is within the focal point. And so I can't think of anything too exciting, so I'm going to draw just an arrow. Okay, so here's an arrow, and it looks like this. All right. Okay, so let's follow our same rules. Well, the first rule is fairly straightforward, which is let's draw a line that is parallel to the principal axis. So let's go along here and get something like this. All right, beautiful. So there's my first ray. But here's the thing is that this is going to bounce off, and it's going to bounce off through the focal point. Now, don't worry too much about the fact that I'm going to run into the arrow itself. That's fine. I know that seems like a weird thing to do, but let's just keep going with it and see where this takes us. Now, the next one's kind of tricky because what I want to do is I want to take my ruler and I want to draw a ray that goes through the focal point. But if I go through the focal point like that, then I'm never going to hit the mirror. So instead, what I'm going to do is I'm going to use my ruler and I'm going to line it up with the focal point, and I'm going to line it up with the top of the object and go away from the top of the object until I hit the mirror. And you can see here's a great example where I'm just going to pretend that the mirror exists at that point. So again, this line here, it lines up with the focal point. Okay, so that's like a straight line there, but I couldn't go that way because I wouldn't hit the mirror. So since it's in line with the focal point, this is going to follow the same rule from before, which is it's going to bounce back. It's going to bounce back parallel like this. Now, if I do my same trick from before, then I guess wherever these lines meet, well, that's where my image is formed. But you can see that the reflected rays are now diverging. And so they're never actually going to meet. This green ray and that purple ray never actually cross paths. But again, this is geometric optics. So while the actual reflected rays don't cross paths, I can think about the lines that they're sitting on. So I'm going to go back to this purple line here, okay? Even though the arrow is going away from the focal point, I'm going to line my ruler up with it, and I'm going to carry this line behind the mirror like this. Okay, so I'm going to draw a little dotted line because the light doesn't actually go there, but I want to kind of know where the line is. And I'm going to do the same thing here with the green ray. So here where I've got that reflected ray that's parallel, I'm going to carry this past the mirror in behind the mirror like this. Now, what do we notice? Okay, well, those lines cross, but they cross behind the mirror. Well, that's okay, because that's the rule we needed to follow, is that where the lines cross, that's where my image is formed. So the top of my object is right there, and the bottom of my object is right here on the principal axis, and now I just need to fill in the blanks. And so it's going to look like this. Okay, so what do we notice about the image? Well, there's a few things. The first thing we should notice, number one, it's now upright. So the image is upright. It's not inverted anymore. The second thing to notice is that it's behind the mirror. Okay, so behind the mirror. It isn't beyond C or between C and F or anything like that. The third thing to notice is that it's large. Okay, it's larger than it was before. And here's the key point. This is it here, is that this is virtual. And what do we mean by virtual? Well, what we mean is the reflected rays do not meet. So the reflected rays do not meet. We can imagine where their lines that they sit on would cross, but the actual rays themselves do not intersect. And so this is a virtual image. You can still see it. It still works. The mirror still works, but you couldn't, for example, project that image onto a screen. There'd be nowhere you could put a screen and capture the image because you'd have to put the screen behind the mirror, and that's not how mirrors work. So the last example here we're going to look at is our center of curvature. And so the last example we're going to look at here is for convex mirrors. Now, for convex mirrors, there's only one space there, so it's a little bit of a giveaway, that you can see that no matter where I put my object, no matter where the object is, well, it always kind of has the same result. Okay, so when I go to set up my convex mirror, the other thing you might notice is that, well, it's a little bit different because the mirror is curving the other way. So while I'm going to put my object over here on the left, the center of curvature and the focal length are over on the other side on the right. So the focal length is over here and my center of curvature is over here. And so over on the left-hand side of the mirror here, I might just draw the same distances I did on the left. Now there's obviously not a real focal point on this mirror because, well, that's not how convex mirrors work. They don't have an actual focal point. So I might just call this F prime and call this C prime, where those are like my virtual focal points, my virtual centers of curvature. And they basically just match, the focal point and center and curvature on the other side. Okay, so I'm just gonna choose something really simple to draw here. I'm just gonna draw like an arrow sitting in front of my mirror, and it doesn't really matter. We'll see here in a second. It doesn't really matter what position we put it in. The results are going to kind of work out the same. So I'm going to follow the same rules that I used before with my concave mirrors. I'm going to draw two rays and see where those intersect, and that's going to tell me what I need to know. So the first thing I'm going to do is I'm going to draw a ray parallel to the top of the object, which kind of goes like this and then strikes the mirror like that. Now just recognize though what's going to happen with this ray. Well, because it's a convex mirror, because it's a diverging mirror, this ray is going to bounce kind of up. But where up is it going to bounce? So I'm going to take my ruler and I'm going to line it up with the focal point that's behind the mirror. And if I line my ruler up, I can see that the ray is going to bounce upwards that way. Now, while I've got my ruler still down, I'm just going to carry this line back through the mirror and just kind of continue along, because as we're going to see in a second, this image is going to be virtual. It's only going to really appear behind the mirror. Now the next thing I'm going to try here is I'm going to try and go through the focal point, right? So I'm going to line up again with the top of the object and I'm going to aim for that focal point. But as I line up with the focal point, of course the mirror is in the way. So even though I'm lined up with the focal point and I'm going towards it like this, I hit the mirror before I reach that. And so that ray is going to bounce back parallel because it was lined up with the focal point even if it never got there. So my ray is going to bounce back parallel to my principal axis. Because it's a virtual image and because these two rays don't converge, there's not going to be a point where they converge. I have to look for, well, where do those lines converge? And because those lines go in all directions, they continue behind the mirror. And you can see that the reflected rays, the lines that the reflected rays sit on, converge behind the mirror. And so right here you can see I've got the top of my image is right at this point right here, and the bottom of my image is on the principal axis, so I just fill in the blanks and away I go. I've got my image. Okay, now looking at this image again, like we can do each time, we should be able to conclude four things about our image. And the first thing is that we notice that it is upright. And the second thing we notice is that it is smaller. Now in terms of location, it is behind the mirror. And as I mentioned several times, it is virtual. Because I've got a diverging mirror. A convex mirror is a diverging mirror. At no point, it doesn't matter where I put my object in front of the mirror, the rays are never going to converge. So you could try this experiment wherever you want and put it beyond C or between C and F, and it doesn't matter. You're always going to get an image that's upright, smaller, and virtual as a result. So that helps us in terms of drawing our ray diagrams and understanding how these rays are going to behave. There is another way to make predictions about how the what the image is going to look like when I look at it from a curved mirror. And we can use the so-called mirror equation to do that. And the mirror equation looks like this. It says 1 over SO plus 1 over SI equals 1 over F. Okay, and so what do all of these things mean? SO is my object distance. Object distance, which is to say, how far in front of the mirror do you place the object? Like we saw with our concave mirrors, where you place the object changes where the image shows up. And so SI is the image distance. And by that I mean the distance that the image appears from the mirror, and that could be in front or it could be behind. And the last thing there is F, and F of course is our focal length, because obviously the focal length of the mirror is going to change where our images appear. And so we can also talk about magnification, because as we saw when we drew our images, sometimes our images appear to be larger, sometimes they appear to be smaller than the original object. So the magnification, which we just call M, is just really just a ratio of how much bigger or smaller the image is than the original object. And so we write it like this. We just say that it's really just the height of the image divided by the height of the object. Now, the height of the object and the height of the image are both going to be proportional to how far they are from the mirror. So we also say that this is equal to negative SI, distance to the image, divided by SO, distance to the object. So we'll talk about in a second why the negative sign is there, but just recognize that if my image is larger than my object, I get a magnification that's greater than 1, and if my image is smaller than my object, then I get a magnification that is less than 1, okay? And so it is important when we're using these formulas, there's some sign conventions we have to be aware of, because depending on what numbers you run through here, you can get negative answers. And so what does it mean if, for example, the image distance is negative or the image height is negative and what have you, okay? So image height, which we call HI, is considered positive if it is upright. So if my image and my object have the same orientation, let's say. So if it's upright, and it's considered to be negative if it is inverted. And of course, this is relative to the original object. And the original object has a height HO, and we're just always, whatever the height of the object is, we're just going to assume that that is positive. So if you're inverted relative to that, you're going to be negative, and if you're upright, you're positive. And then so for the image distance, the given image distance, which we call SI, it is considered positive if the image is real, and it is considered negative if the image is virtual, okay? So notice I'm not saying in front of the mirror, behind the mirror. I'm talking about real and virtual, and that's going to become an important distinction later when we talk about lenses, okay? So if the image is real, then it gets a positive SI, and if it's virtual, then it gets a negative SI. And that can help you understand why this negative sign showed up in this magnification formula, which we'll see in a second. So I've got an example here. We're just going to do one, and we've got a 5 centimeter tall object placed 8 centimeters in front of a concave mirror that has a radius of curvature of 20 centimeters. Okay, lots of numbers. Great, thank you. Find the location and height of the image as well as the magnification. Now, because this is geometric optics, you could actually solve this entirely geometrically. If you drew like a really precise 2-scale diagram, you could actually just measure the height and the distance, and that would be the correct answer. I am not that confident in my drafting skills, so I am going to sketch it out roughly, and then from there I'll already kind of know what the answers should be approximately, and then I'll do the calculation and see if I got the right answer. So it is helpful to kind of be able to sketch it out a little bit ahead of time. So the first thing I notice is that my center of curvature is 20 centimeters. So I'm just going to again do this to scale. So for me, I'm actually going to divide that in 2, just so I've got so that I'm not taking up a whole sheet of paper. Okay, so I'm going to put my center of curvature over here, which means that relative to that, my focal point will be there. So my center of curvature is here, and my focal point is half of that. And maybe I'll just label this right here. The focal length, you can see here, F is going to be 10 centimeters. Okay, the object is 5 centimeters tall and it's placed 8 centimeters in front of the mirror. So again, I'm just kind of sketching this out approximately, but if this distance is 10 centimeters, then my object is approximately here. Okay, so the object is 5 centimeters tall, so my object height of the object is 5 centimeters, and then the distance SI, which I talked about there, SO, the object distance is 8 centimeters. So again, and we can just sort of rough this out. It doesn't have to be perfect, but let's just kind of predict what our image is going to look like. And so I'm going to do that by drawing a line from the top of my object going towards the mirror. I know that that's going to bounce through the focal point. So it's going to bounce through this way. My next ray I would draw would be going through the focal point, but I can't hit that. So I'm just going to go line it up with the focal point and go away this way. Okay, and I'm going to hit the mirror up there somewhere. And this is far from perfect, but that's going to bounce back parallel. And those are going to diverge. Those rays are never going to come together. So I'm going to carry the reflected rays back behind the mirror, and I'm going to carry this other reflected ray behind the mirror. Okay, and so I can see here that my image is going to appear something like this. Now again, I just sketched this out roughly, but I can already see that I should get an image that's upright. It should have a bigger image distance, right? So this is my image distance right here is my SI. My SI should be negative because it's virtual, and then my HI should be bigger than 5. Okay, my magnification should be larger than 1. So I've already kind of roughed out what my answer could be. If this was a multiple choice question, I might even be able to just get the answer just from the selection of what they've given me. So unfortunately for you, it's not. And so we actually have to do some work here. So 1 over SO plus 1 over SI equals 1 over F. And I'm looking for the image distance. So solving for SI, 1 over SI equals 1 over F minus 1 over SO. And just be really careful that we can't just flip everything over. It's not how inverse terms work when they're separated by a subtraction. So 1 over SI is going to equal 1 over 10 minus 1 over 8. And because it's been a while since I've done fractions, I can have a common denominator of 40, so I could say that this is 4 over 40 minus 5 over 40, which gives me 1 over SI equals 1 over 40, negative 1 over 40. And so that just means that SI is going to equal negative 40 centimeters, which is great, because that is, you can see that I kind of predicted that here from my picture. My SI should be bigger than 10, much bigger than 10. And also it's negative because it is a virtual image. And so that's good. 2 good bits of good news. I now want to find the height and magnification. And so remember, with the magnification, we can find that 2 ways. So I could say magnification, I'm going to use, I know SI and SO, so I'm going to use that. It's negative SI over SO. And so that's going to be negative times negative 40 over 8. And so you can see that works out to be 5. Now, 2 things to notice. Number 1, it's positive, and it's positive because my image is upright. So that negative sign out front kind of mattered. The other thing to notice, though, is that there's no units here, right? So there's no units because magnification is just a ratio. This is ratio of distance or height. So it doesn't have a unit. And so I've got my magnification. So last thing I want to do here then is find my, I know my magnification also equals HI over HO. So then HI equals the height of the object times the magnification, which sort of makes sense, hopefully. So I go from 5 times 5, so I've got a height of 25. Now this is measured in centimeters here for my object. Okay, that is it for our lesson on reflection.